Welcome back, everyone. Boy, that music is so powerful. You'd think I'm gonna turn the world upside down with that kind of intro. Anyway, this is a serious presentation. I've been doing a lot of work on multiple occasions. I've come up to the aqueduct site and I've established six sites from which I've observed a new target that's almost at eye level, just 82 feet differential, is slightly higher. And before we dive into the data, here's some clips from some of my adventures. The aqueduct is a really awesome site to do these kinds of experiments. On this particular day, the water was very still. So this is my Theodolite, a 2 arc second Theodolite. I'm really pleased with it. I picked it up on sale on Amazon. Somebody returned it brand new. So looking through the telescope, this is the target that I've chosen, this rock outcropping. It's almost at eye level. According to Google Earth, the elevation at the top of that rock is just 82 feet above the observation locations along this walkway here. So it's almost at eye level. So I've done forward and reverse measurements at all the sites and gathered a lot of data, which I'll show in just a little bit. So the poppy fields were in bloom and it's just incredible. I've been up here a few times looking at the poppy fields, and I love this walk by the aqueduct. It's incredible. So I walked quite a bit, and the view is just so exhilarating. I just can't get enough of this wide open area. Just incredible. But let's have a look at the data to see what it says about the radius of the Earth. Okay, so here's the data. Lots of it. Let me walk you through everything so you understand what I'm doing, okay? So I've made the observation from different sites. First column records that. Then that's the distance from the target in the second column. Then we've measured the zenith angle. Now this angle here is the corrected one based on the forward and reverse observations and adjusting for the air misalignment. Okay, and then I subtract 90 degrees to get the elevation angle, which is relative to the local horizontal. Okay, so it's negative because it's below the horizontal. Now, to calculate the radius of the Earth, we need to get the angle, the elevation angle to the chord. And that's the next column, the chord elevation angle. Okay, and in a previous version of this video, I actually had a mistake. I forgot to convert radians to degrees. So I was adding basically apples to oranges. So that's not good. So thank you to whoever pointed that out. Okay. So we have the chord angle. Now we can calculate the Earth radius. So to do that, look at the diagram, the picture there in the lower right. The blue is the chord length, okay? And so we have two, we can bisect that and we have two triangles, right? And there's my equation, simple trigonometry. And when we do that, we get, and then of course I average all the results and I get 4,394 miles with a standard deviation of just a few miles. Now the accepted radius of the Earth is 3,959. So we're fairly close here. Now we haven't assumed any refraction. This is just pure geometry here and angular measurements. But a good question to ask is, have we really measured the radius of the Earth? I mean, this area in the Mojave Desert is fairly flat. Have we measured the radius of curvature of this flat area? The answer is no. We've made some measurements, obviously, but we're relying on data extracted from Google Earth. The target altitude and the altitude of the aqueduct walkway, which is fairly level. All right, those numbers come from a spherical coordinate system that Google Earth uses, or ellipsoidal. Okay, so what we've done is we've really exposed the value that was used to encode those values. To really understand this, have a look at this graphic. So there's flat areas on the Earth, and this graphic depicts such an area. I've drawn that blue curve there, fairly flat, okay? And there's two altitudes above mean sea level, H1 and H2. Now, if we take that segment and we measure more altitudes across it and we plot that on a graph as a function of angular distance, well, what do you know? That flat area plots as a curved line curving upwards. So we've really turned things upside down. You know, so it really depends on the coordinate system, right? We used the coordinate system and he gave us some altitudes for our target and the observational sites. And all we've done is really measure the angle and expose that radius that was used to encode this data. That's all we've done. We really haven't measured the radius of curvature in Antelope Valley. Not at all. You know, that area is very flat. Now, there is something we can do, and to help us get a better understanding, I've zoomed in on this graphic, okay? I'll show this a little bit later in this presentation. We're trying to see if there's any gravitational vector divergence which the globe predicts, okay? And so as we move along a flat segment and we're measuring the same target, we should see a change in the angles, okay, due to positional change or geometry change, but also due to the gravitational vector changes, okay? So it's an interesting way to try to measure the radius of the Earth indirectly by looking at the divergence in the gravitational vector utilizing a flat area. In a previous experiment, I've used a telescope with an infrared camera and an inclinometer to try to measure the divergence of the gravitational vector, and I concluded there was no divergence. Now, it's important to pick a target far away to minimize geometric variations, as you'll see later. But because I'm using the Theodolite and I'm sighting in the visible spectrum, I had to choose a target close by. So this second experiment I'm presenting here is somewhat different. Closer target, sighting in the visible spectrum, and there's some subtle differences there that can produce different results. But I like the accuracy. The accuracy of the theodolite is an order of magnitude um, better than my other contraptions. So I'm really pleased with it. Now let's have a look at refraction, because that's used to make up the difference between the theoretical and the observed. So we know there is refraction, and reading the underlined text there, since the line of sight in terrestrial refraction passes near the Earth's surface, the magnitude of refraction depends chiefly on the temperature gradient near the ground, which varies widely. The highlighted text says, as a common approximation, terrestrial refraction is considered as a constant bending of the ray of light or line of sight, in which the ray can be considered as describing a circular path. So there's refraction, and it's bending that line of sight. But which way is it bending? Well, there's a dilemma. Let's look at two possibilities. So this graphic illustrates the two ways of thinking about this and accounting for the measured angle differences. If we believe we live on a globe, all right, there's a curvature drop due to the globe of 16 arc minutes and 9 arc seconds. So we come down using those green arrows, the vertical arrows. So we come down to 13 arc minutes and 17 arc seconds. But we measured something only 4 arc minutes and 26 arc seconds below the horizontal. So there must be downward refraction bringing that up. Okay, so that's the globe way. Now, if you believe you live on a flat Earth, you come down from 2 arc minutes, 52 arc seconds, where the peak should be relative to our horizontal. You come down due to upward refraction phenomena. So one model relies on a dropping curvature and downward refraction, and the other one relies just on upward refraction. And as often is the case, the truth is somewhere in between. A side view allows us to understand the two models better. So the flat Earth requires or needs light to curve up, okay? And the globe model requires light to curve down, okay? So the dotted line represents where we observe the peak. So it's down from where the flat Earth would say it should be without refraction. And it's up from where the globe says it should be. All right, so which model is correct? Well, in the inset, I have some temperature gradient profiles there. And looking closely at what happens close to the ground, there's a stronger gradient there on a hotter day. And yeah, that kind of indicates that light really curves up. So we don't really know what happens in the volume of air that light propagates through to reach our theodolite. The measured angle, theta, is a function of many variables, So if we now vary one of those variables, we gain additional insight on what is happening. You see, most of the accumulated curvature in propagation has occurred over a large distance, and now we're just moving just a little bit. All right, so we're not really interested in the absolute measurement. Now we're kind of interested to see how that variable affects the function. This graphic illustrates the benefits of picking a target that is close to eye level to minimize the angle variation just due to geometry change. In the top part, notice the target is higher, and as we move back, there's quite a bit of change in angle observed from the three sides. But in the lower part of the graphic, notice the angle doesn't change much. Now, if we move the target farther out, we further minimize that angle. Now, why do we want to do that? Well, as we minimize the angle variation due to geometry, we begin to expose the angle variation due to the gravitational vector. All right. Some people wonder, how can we measure the gravitational vector with a telescope? Well, it's not just a telescope. It's a telescope and an inclinometer. Inside the theodolite, there's a highly accurate electrolytic inclinometer. All right, so we're leveling the theodolite at the different sites relative to the local gravitational vector. So we'll begin to see in the data this gravitational vector variation if we live on a globe. Well, does it show up? Now here's all the data plotted out, and wow, look at all that variation. What's going on? Jeez. All right, so different data sets, different taken on different days, times, and different temperatures. And the top straight blue line, that's the globe calculation. All right, just a differential calculation. The angle is basically increasing from our reference location at site 1, which I've set that to 0. All right, so the angle should increase between the gravitational vectors. When we associate the temperature with the curve, we begin to see a pattern that's quite interesting. Notice the temperatures for each curve starts out at 80, the orange one. Then it goes down 75, 70, 65, 60, 55. Wow! Isn't that incredible? Now let's change the radius of the Earth on the spreadsheet and move that blue line just to curve fit. So here we go, 3959. Let's change that to 5,000. Boom! The blue line moved. Let's go up to 6,000. Boom! Whoa, look at that. Now let's go higher to 7,000. Boom! Wow, almost in between those two curves. 8,000. Okay. Let's go up to 9,000. And then let's try 10,000. Let's see. Yeah, wow, look at that. And now let's try 12,000. Boom. Look at that. Isn't that crazy? So a relationship we notice is that a lower temperature produces a larger radius. Isn't that incredible? We were supposed to kind of measure the divergence of the gravitational vector or the lack thereof. And notice all that variation, which is pretty much due to temperature. That's just incredible. Choosing a target that's almost at eye level turns out to be problematic from a refraction point of view. Okay, as the simple example shows based on Snell's law, as the incidence angle measured from the zenith increases close to 90 or horizontal, notice the angle difference increases, right? The refraction, the angle between theta 1 and theta 2. So unfortunately, a lot of flat earthers do experiments at these low grazing angles, uh, which is very problematic. We should be looking at steep angles towards the surface, which I've done from my aerial photography and using photogrammetry. And that's when we are stunned that the earth is extremely flat. I've gone back to the aqueduct on another occasion, and I picked a power pole that was much higher, so I can illustrate the effects of refraction. In order to create steeper angle observations, I've chosen a power pole weighing the distance. Now I'm looking west. The target for the previous experiment was behind us. Now we're looking the other way. And you'll see it through the telescope here in a second. There it is. Okay. And here is a different site. So the sites here are totally different than the other ones. And there's the pole again. Now here's the results, folks. Quite incredible, but this is to be expected. Notice how refraction really picks up and starts dropping the calculated height of the pole. Now let's walk through the chart. So fairly simple calculation. So I have the distance I've extracted. I've measured the zenith angle. Of course, that's the corrected one based on forward and reverse. And then I calculate the pole height using that equation. Notice I'm using the cell B2, which is the distance, okay? That multiplied with the tangent of the angle. And 90 minus D2 gives me just the elevation angle that I want, okay? And then I convert that to radians, all right? So that gives me the height of the pole, all right? And when we look at the chart, when we're close in, so the measurements started far away, and then I work my way closer to the pole. And so pretty soon it starts to level off and we get accurate measurements. Now, like I mentioned, the site locations are different than the ones before. Now, data point 4 from site 4, I've excluded from the curve fit there. Why did I do that? Well, look at the image there. It was barely visible above the hill. And so there's this phenomena that occurs, okay, where a large mass in front of a object tends to bring down the angle. We've seen that in a previous video of mine. And notice the difference it makes. It's significant. So now we see this typical inverted refraction curve, right? We kind of measure accurate height and then all of a sudden it starts decreasing rapidly. That's because we're approaching a shallow angle. And at site 3, if you look up there, it's 89 degrees. It's around 1 degree elevation. And that's where things really begin to, that's where refraction really takes over drastically. Now let's see what the Earth model would predict. So I've added the columns in red with the globe calculations. This is a busy chart. It takes some time digesting it, but I'm showing the equation for the globe pole height that I plotted with the green line, okay? Now that's missing a term, a theta 3 adjustment due to the vertical drop. I left that off because it makes it too complicated to follow. If you look in the lower right inset there at the geometry, and spend some time, you'll start making sense what's really happening. If we're at point 1, P1, um, and lined up with the pole, you know, on a flat Earth with no gravity divergence, we would measure along that magenta line, okay? But then, because we're on a globe, the vector leans back. There's an angle tilt to it. So the zenith angle increases, okay? Thus the elevation angle gets smaller. So the pole would appear to be smaller. In addition, there is a vertical drop as well, thus making the pole appear larger. So the two calculations work against each other. So the final answer is the dotted black line in the graph on the left. I just drew that in based on my calculation of how much vertical drop there is, about 0.8 of a foot in that distance. So yeah, the two curves are not quite the same, and we've also observed this from the air. Looking down at the ground, same phenomena. It appears to be flat and then it begins to roll off in the distance. So refraction needs to be understood and mitigated, and we mitigate that by increasing the observational angle. Okay, and I'll have a future presentation with more photogrammetry work that I've done. I have a lot of imagery. Now, obviously, there's a difference in locations between being way up at 35,000 feet and being on the surface of the Earth. Gradients are different, but the same principles apply. So based on the terrestrial refraction models, I am persuaded that light curves up. So the flat Earth model has a lot more merit. Now the 12,000 mile radius reminds me of the observations I made from the air in Florida. If you haven't seen that video, you can find it on my channel. Quite amazing views in infrared. We got off a cruise ship and it was really cold, probably around 55 degrees, and curiously that correlates with the previous charts, and I calculated the radius at 12,180 miles. Isn't that incredible? I hope you've enjoyed this presentation, folks. Our world is incredibly mysterious, and if you've enjoyed this video, don't forget to hit the like button and make sure you subscribe if you haven't already, and keep watching. We've done a lot of vertical analysis, but I'm moving more into horizontal analysis. Thanks for watching, everyone. Enjoy this incredible soundtrack one more time.